Hi everyone, in this lesson we're going to look at polynomial functions and models. So basically a polynomial function in one variable is a function that takes on this form right here, where your a sub n's are all constants or numbers, and when they are attached to a variable we call them coefficients. And the exponent always has to be greater than or equal to 0, so no negative exponents, where x is always a variable, okay? As long as a sub n doesn't equal 0, that is going to be the lead coefficient, and n is the degree of the polynomial. Okay, each of the pieces that make up the polynomial are called terms. So this is a term, and this is a term, and so on. The leading term in the above polynomial would be a sub n x to the nth power. And then the constant term, or the term that's just a number, is your a sub 0. When we write polynomials, we usually express them in standard form. So that's when we have the term that has the highest exponent all the way down to the lowest. In the next set of examples, we would determine whether each of the expressions is a polynomial, and if it is, we want to identify the leading term, the leading coefficient, and the degree. And if it's not, explain why not. So if I look at letter A, I have terms made up of coefficients that are numbers, and my only variable is x, and my powers are all integers, so 3, 2, no negative powers. I don't see any variables in a denominator, so this is a polynomial function. It does take on this form right here. So I have to explain what the leading term is and the leading coefficient and degree. So it is in standard form because my highest exponent or power goes first and then it decreases. So my leading term would be 5x to the third. So I'll call that my LT. So if 5x to the third is my leading term, it contains your leading coefficient and it contains your power. So the leading coefficient would be 5, and then the power or degree would be 3. So 5 is your lead coefficient, and 3 is the degree. So this polynomial is degree 3. In letter B, I have f of x equals x plus 2 minus 3x to the fourth. This is a polynomial because none of my x's are in a denominator. All of my powers are integers, so x to the first, x to the fourth, and this would actually be x to the 0 power. So anything to the 0 power is 1, so it's not written. And it's just not in standard form. So we're going to put it in standard form. So yes, this is a polynomial. And if I was to rewrite this in standard form, I would want the lead term to go first, which would have the highest power. And then I'm going to decrease powers. So the next highest power would be x to the first. And then like I said, this 2 really has an x to the 0. X to the 0, any power to the 0 is 1. So we don't actually write it. So that's important to remember, that anything to the 0 power is 1. So that's why when we express this, we leave out the x to the 0. So the function would really be written as f of x equals negative 3x to the fourth plus x plus 2. So my lead term would then be the negative 3x to the fourth. And again, if I need to find my lead coefficient, it's negative 3, and my degree would be 4. So this is your lead coefficient, and this is your degree. Letter C is not a polynomial function, and the reason is because of the denominator containing a variable. Okay, so fractions are okay, we just can't have fractions with variables in the denominator. So for instance, something like 1/4 x squared is still a polynomial because x squared, I can place it on the top and put it over 4. So that's okay. But if you had 1 over 4x squared, that would not be a polynomial function because any variable that's in the denominator really has a negative power. So if you'll recall from algebra, if I was to take this x squared and place it up top, it would be x to the negative second over 4. And remember, we said for polynomials, your powers all have to be greater than or equal to 0. So that tells me why that is not considered a polynomial function. Okay, you can try A through C on your own, and then you can unpause the video when you're ready to move on. So every graph of a polynomial function is smooth, which means it has no sharp corners or cusps, and it's continuous. There's no gaps, there's no holes in the graph. So think of continuous. If a function is continuous, if you were to place your pencil at one end and draw the curve, you don't have to pick your pencil up to continue drawing the curve. However, in this graph, this is not continuous because if I started here and moved along the curve, I would have to pick up my pencil to continue on with the graph. So that's an easy way to tell if a function is continuous or not. You can also see here that there's a gap between the two pieces. We have corners, we have cusps, which are kind of like sharp edges, and then there's holes that are signified by open circles. Polynomials generally consist of hills and valleys. We kind of talked about those. Those are called turning points or inflection points. And here's an interesting fact, that if you have a polynomial function of degree n, then the graph has at most n minus 1 turning points. So what that means is, let's say I had a graph of x to the third. My n is 3. So that means that that polynomial will have at most 3 minus 1 or 2 turning points. If I was to graph an x to the third, you'll see here that it's only going to turn in 2 places. So x to the third looks like this. And in fact, here you can see that there's only one place where it actually turns, right at 0, 0. So keep in mind that's the maximum number of turns. Okay, so if I have a constant term, like the number 5, which is actually a polynomial, it would have n minus 1 turning points at most. So keep in mind, you really have x to the 0 power, right? So I can't subtract 1 from 0. I would end up with a negative number of turns. So there are no turns here. Remember, if you graph a constant function, it's just going to be a horizontal line. It's not turning. If I was to graph a function that had a degree of 1, we know that's linear, and it has 1 minus 1 or 0 turning points. If you graph a straight line, it will not turn, right? It's either going to always be increasing, always be decreasing, or constant. A quadratic we know is shaped like a U, a parabola, and we know that it would have 2 minus 1 or 1 turning point at most. And we know that in a parabola, it's either a max, so it's turning, it's decreasing and then increasing, or it's a min, where it's a concave down, concave up rather, where it's increasing and decreasing. And then you've got a degree 3, so it'd have 3 minus 1 or 2 turning points. Degree 4 has 4 minus 1 or 3 turning points at most. And degree 5, which we call a quintic polynomial, has 5 minus 1 or 4 turning points at most. Remember, that's the maximum. It doesn't mean it has to have that many. It's just the most it can have. Okay, so let's take this polynomial here and let's figure out the leading coefficient, the degree, and the maximum number of turning points. So I'm just going to plug it into Desmos. Okay, so as you can see here, if we're looking at the number of turning points, it actually has 1, 2, 3, 4, 5 turning points, which makes sense because it's a degree 6. So it will have at most n minus 1 or 6 minus 1 turning points. So it has 5 turning points here. Every place where there's basically like a dot in the either in the valley or on top of the hill. So there's 5 places in which that occurs. And this is in descending order, standard form, so it's easy to pick out my lead term, which would be 2x to the 6th. So that tells me that my lead coefficient then would be 2, and my degree would therefore be 6. And if I want to find the maximum number of turning points, it's going to be n minus 1 maximum. So n is 5. N is 6. And there's 6 minus 1 or 5 turning points maximum. And as we saw, that did occur. Next, we're going to look at something that's really important that's going to be vital in understanding how to graph polynomial functions, and that's what's called end behavior. It's literally how the graph behaves on its ends. So to determine end behavior, we need to look at 2 things. We need to find the leading term, and from that leading term, we're going to look at the sign of the lead coefficient. Is it positive or negative? And the degree. All we have to ask ourselves is the degree, n, is it odd or is it even? So when the lead coefficient is positive, it's going to be facing up. So this needs to change, by the way. That should be a greater than symbol. So let me make that in red so it stands out. This should be a of n is greater than 0. And when the lead coefficient's greater than 0 or positive, and even, when the degree is even, it's going to have both of its ends pointing up. If a of n is less than 0, so this should be a less than, and the degree is even, it's going to point down. So in other words, here's an example. Let's say we had positive x squared. Okay, so a of n, the lead coefficient's 1. 1's bigger than 0, and my degree is even. So it's going, both ends are going to point up. If I have a negative x squared, right, we know that that's a parabola facing downwards. So my lead coefficient's negative 1. It's less than 0, and my degree is still even. So it points down on both ends. If n is odd, let's say x to the 3rd. Okay, so when your lead coefficient is greater than 0, you're going to have your, and the degree is odd, you're going to have one end pointing up and the other pointing down to the left. So they're going in opposite directions, right? O for odd, O for opposite. So remember, anytime a degree is odd, the ends are going to point in opposite directions. As long as the lead coefficient's positive, it's going to point up. If the lead coefficient is negative, it's going to point down. So we want to change this to less than. Okay, so if I had negative x cubed and you graphed it, you would see that the left side would point up and the right side would point down. So let's take a look at that. So here's positive x cubed. You're going to see that it's going to point to the right on the right side, and it's going to point down to the left on the left side, right? So that's a positive lead coefficient and odd degree. So it's going to go in opposite directions. As I said, the positive, the right side's going to point up, the left side's going to point down. If I switch it to a negative x cubed, you're going to see that it's just going to reflect, and it's going to be the opposite now. So now on the left side it points up, and on the right side it points down. And if you compare that to your notes, right, a negative lead coefficient with an odd degree is going to point in opposite directions. It's going to point downwards. Notice though, I could change my degree to anything odd, like I could even just make this a negative x to the 1st, and it's going to do the same thing. It's going to point down to the right. let's say I make it negative x to the fifth, it's still going to point down to the right. So these polynomials, no matter what their degrees are, as long as they are all odd and they are negative, they're going to point down to the right. So another important thing we want to look at is identifying the real zeros of a polynomial function and then what's called its multiplicity. So you've actually worked with real zeros before. If you take a look at this graph, right, and this is a polynomial function, what do you notice about the function? So take a second, pause the video, write down what you notice about it. And all I'm really looking for here is the fact that there are 4 places that the graph crosses the x-axis. And if you remember, those are called x-intercepts, right? So there's 4 x-intercepts. And this is just the graph crosses or it touches the x-axis at those points. So as you can see here, the graph doesn't always go through, right? It might cross through, but then here it only basically touches that point. It doesn't really cross through. It doesn't go through the axis. It hits the axis, changes direction, and keeps going. Then it crosses through. Okay, so it's really easy to locate the x-intercepts of a polynomial function when the polynomial function is factored completely. And we're going to do this by taking equations and solving them and applying the zero product property. Okay, so what you want to gather from this information is that real zeros, another name for real zeros, are just intercepts. Okay, and the intercepts are on the x-axis in this case. And that is where the function, how do you find an x-intercept? It's where y equals 0. That's where the function equals 0. And in some places, the graph is going to cross through the x-axis. In other places, like here, it's crossing through. In other places, it's just going to touch the graph there and kind of turn directions. So like it would be if you were taking a roller coaster, you would be going up the hill and then down the hill. So it changes directions there. Okay, and we said that we can find the x-intercepts when the polynomial function is factored. So if we take an example here, we have f of x equals x minus 1 squared times x plus 3. And I want to find the x-intercepts. Okay, so how do I find an x-intercept? I make y equal 0. So I'm going to set that function equal to 0. And I'm going to solve. So I'm going to apply the zero product property, remember, which says if you have factors that multiply to give you 0, one of those factors has to equal 0. So I'm just going to take both of my factors, x minus 1 squared equals 0 and x plus 3 equal to 0. And now I'm going to solve. So if you solve this, it's already set up so that one quantity is being squared. So how do you undo a square? You take the square root of both sides. And if I take the square root of both sides, what am I left with? X minus 1 equals, normally you get a plus or minus when you take the square root of both sides of an equation, but plus or minus the square root of 0 means nothing, right? So it's just going to be 0. And then solve for x. So x would equal 1 here. And then here we would subtract 3 and you would get x equals negative 3. So one of your intercepts is 1, 0. The other is negative 3, 0. What's important though is that you had a squared here and you really had an exponent of 1 here. So when we're finding x-intercepts, the degree tells us what the graph is going to be doing at that point, whether it will be crossing or whether it will be touching the graph. Okay, these are also known as the real zeros. Okay, so they're the zeros or the x-intercepts of that function. Here's what this tells us. Okay, so what we want to remember is that r is a real zero of a polynomial function f. What that means is if I was to take 1 and plug it into this function, it would give me 0. If I took -3 and plugged it into this function, it would give me 0. Those values, we call them r, are also x-intercepts of the graph. What that also tells us is that x minus r is a factor. So look, if I take r and then I do x minus this, I get a factor. X minus -3 turns into x plus 3. That's one of my factors. And r is what's called a real solution to the equation f of x equals 0. So if I said solve this equation, those would be your solutions, 1 and -3. What it also tells me is where the graph crosses or touches the x-axis. So when the function's factored, if x minus r occurs more than once, like it does here, it occurs twice, r is called a repeated or multiple real zero of f. So this is a repeated zero because it actually comes up 2 times. Here, it only comes up 1 time because it's x plus 3 to the first. So we also know that as multiplicity, okay? So for instance, 1 is a real zero with multiplicity 2. And -3 is just a real zero. There is no multiplicity. It's really multiplicity 1, but we don't really express that. So if r has an odd multiplicity, the graph is going to cross the x-axis. If it's even multiplicity, the graph will touch the x-axis. So what that means is, right here, since this is an even multiplicity, if I was to graph this, right, it tells me that even multiplicities touch the x-axis. So when we look at the graph, we're going to see the graph touch the x-axis at 1, but it's not going to pass through it. And then here, since that's multiplicity 1, 1 is odd, the graph will actually cross through the x-axis at that point. Okay, so let's take a look at the graph really quick and see what happens. Okay, if I was to plug this in, I would have x minus 1, and then it's squared, and then times x plus 3. Okay, as you can see, here's the two x-intercepts. At -3, it was an odd multiplicity, right? It only occurred 1 time. What does it do? It crosses through the x-axis. But if you look here, where x equals 1, it touches the x-axis there. So it hits 1 and then it changes direction. So it's like you're coming down the roller coaster, it hits the 1, and then you're going up the roller coaster. So that's going to be very important when you're graphing polynomial functions in the next lesson, to be able to identify the zeros and then to understand its multiplicity. And when it's odd, it's going to cross through, and when it's even, it's just going to touch the graph. Hi all, in this next part of the video, we're going to look at polynomial functions, and we're going to find the zeros and state the multiplicity and determine if the graph will cross or touch at each zero, and then also look at the end behavior. So in this first problem here, we have this polynomial, and I want to find the zeros, which remember just the x-intercepts. So I'm going to take my expression and just set it equal to 0. And remember that we're going to apply the zero product property, which just means take each of the factors and set it equal to 0. I don't have to worry about setting 1/10 equal to 0 because it doesn't, right? So we're just going to take x minus 2 to the third and make it equal 0, 2x minus 1 equals 0, and x plus 2 squared equals 0. And my exponents tell me my multiplicity. So here we know we're going to have a repeated root of 3. It's going to be a multiplicity of 3. That just means that when you solve this and set it equal to 0, it has 3 answers that are the same. So if you solve for x here, you're going to get 2. But because of the 3, there's really 3 2's. So x equals 2 has a multiplicity of 3. And then 2x minus 1, if I solve that for x, I get 1/2. And that multiplicity is just 1. And then x plus 2, if I set that equal to 0 and solve for x, I get -2. And that multiplicity is 2. Okay, and again, the multiplicity comes from the exponent. Okay, so now the multiplicity also tells me whether the graph will cross or touch the x-axis at that point. So remember, if the multiplicity is odd, it's going to cross the x-axis at that point. So the two odd multiplicities would be this here, because it's 3 is odd, and this here, because it's got a multiplicity of 1 is odd. So it's going to cross the x-axis there. So here it's going to cross at x equals 2, and here it's going to cross at x equals 1/2. And you'll see that in the graph. And then even multiplicity means that the graph is just going to touch the x-axis at that point. So it's going to touch the graph at x equals -2. So you're going to see here, if I pull up the graph, you can see here how it's crossing at 1/2 and at 2, because those both had an odd multiplicity, and it's touching the x-axis at x equals -2. So it's kind of hitting the -2, and then it's bouncing off. And this is going to be useful when you're graphing polynomial functions, okay, in addition to finding the end behavior. So that's the next thing I need to do. So I found the answer. My zeros were 2, 1/2, and -2. And then it crosses and touches at certain points. And then letter C is the end behavior. So for end behavior, remember, I need to know two things. I need to know the leading coefficient, if it's positive or negative, and the degree, if it's even or odd. So my leading coefficient here, right, I would have a 1/10 x, and then a 2x, and an x. So if you multiply them, you would get 2/10, and then it would be x to the 6th power, because you have an x cubed, an x to the 1st, and an x squared. So if I add those, I get x to the 6th. So my degree is 6, which is even, and my lead coefficient here, it's positive, right? We said positive 2/10. So when it is positive and even, remember that it's going to point upwards on both sides. So think of x squared, right? It's positive and even, and it's a parabola that's concave up, so it's pointing up. So when I write my end behavior, I'm going to express it like this. I'm going to talk about the limit as x approaches positive infinity of f of x. So that just means on the x-axis, so if we look at the graph, if we were to go towards positive infinity on the x-axis, what is the graph doing on that end? Well, on the right side, it's pointing up. So f of x is always going to approach positive infinity. So this is going to equal positive infinity. And the limit as x approaches negative infinity just means as you are walking along the x-axis towards negative infinity, again, if you look at the graph, what's happening to the graph? It's always increasing towards positive infinity forever. So the limit here is going to also equal positive infinity. Anytime you have, you're talking about end behavior and it's positive and even or negative and even, you're going to get the same answer for both limits, okay? Because remember, both sides are going to be going in the same direction. It's when you have odd powers that it's going to go opposite. So you'll get two opposite answers. One will be positive infinity, the other will be negative infinity. Okay, let's try one more. So here we have f of x equals x cubed minus x squared minus 2x. So the first thing I need to do is find the zeros. So I'm just going to set this equal to 0. Okay, and this is not factored for me like letter A was. So I'm going to go ahead and factor it. And here we can factor out an x, and you're left with x squared minus x minus 2. And then I can also factor the inside here. So two numbers that multiply to give you -2 that add to -1, and we get x minus 2 times x plus 1. Okay, and I'm going to set each of these factors equal to 0. And here, as you can see, we don't have any powers other than 1. So for each of those, it has a multiplicity of 1. 1 is odd, so that means it's going to cross. So it's going to cross at x equals 1, it's going to cross at x equals 2, and it's going to cross at x equals -1. So here are your zeros, and it's going to cross in each place. So if we were to actually graph that, you'll see, so if I plug in here, I have my x cubed minus x squared minus 2x. You can see at each of those zeros or x-intercepts, the graph goes right through and crosses. Also take a look at the end behavior. It is going in opposite directions, right? And that makes sense because our degree is a 3, it's odd. So when we're looking at end behavior, my lead coefficient here would be 1, so that's +1. And my degree is 3, which is odd. So remember, positive and odd, the right side's going to go up, the left side's going to go down. They're going to go in opposite directions. So here, if you go to the right on the graph, as x approaches positive infinity, f of x is also going to approach positive infinity. It's going to point up. And as x approaches negative infinity, as you go left on the graph, that's negative infinity. Let me make that more clear. F of x is going to approach negative infinity, so they're opposite for that one. Okay, and you all can try the next problem on your own if you take a look at those examples from above. And in this last problem here, we have a function, okay? And again, you can try this on your own. Looking at the examples from above, so you want to talk about how many turning points does this have? You want to find the y-intercept algebraically. We talked about all of that in the last chapter and before. Find the zeros or the x-intercepts and their multiplicity, and then discuss the end behavior as well. Okay, and the only other thing I want to point out to you are what power functions are. There are functions of degree n, and they're in monomial form. So mono means 1, right? It's one polynomial. Okay, it's going to resemble something like this. So if you had like x squared, that's called a power function. -5x cubed, 1/2 x to the 6th. Okay, and what's important to remember is that polynomials resemble a power function when you have large values of the absolute value of x, specifically with end behavior. So x squared, I know it's positive and even, so the graph, remember, is going to go up on both sides. So if I was to take x squared, a power function, and let's say add on to it, like something like this, if you graph that equation, it's going to resemble the power function. So even though it will look slightly different, it'll go through the x-axis in different places, it's going to contain the same end behavior. It's going to approach positive infinity as x approaches positive or negative infinity. Okay, just like this one is negative lead coefficient and it's odd. So remember, negative and odd, it's going to point up to the left and down to the right. Okay, so even if I created another equation using that power function, like something like this, it's going to contain the same end behavior. Okay, that's it for this lesson. Please feel free if you need to go back and review to do that. If you have any questions, please reach out to me.